Hello, my name is Emily from the Rensselaer Polytechnic Institute Engineering Ambassadors, and today we are going to be talking about jet engines. I am sure many of you like cars, or at least have been in one before, maybe when your mom or dad drive you to school or the supermarket. Can anybody tell me what powers this car and makes it move? Right, the engine. Now, the unit for measuring how powerful and strong an engine can be is called horsepower, because cars used to be carriages pulled by horses. Back then, it was literally horsepower. So can anyone name some fast cars that have a lot of power? Yes, Ferrari. More specifically, the Ferrari LaFerrari, which is a really fast and powerful car. Now, how much horsepower do you think the Ferrari LaFerrari, like the one on the screen, has? 800 horsepower. Now, if the engine of the Ferrari has 800 horsepower, how much horsepower does the jet engine of a Boeing 777 have? The jet engine of a Boeing 77 airplane actually has 110,000 horsepower. That is the same as packing 130 Ferraris into that one jet engine, and an airplane has two of those. Today, we are going to talk about jet engines in 3 stages. First, we will discuss the parts of an engine and how the engine works. Then we will talk about how engines are tested to make sure they perform well. And finally, we will see different types of engines and the industries they can be used in. Let's start with engine components. So the first part of the engine we are going to talk about is the compressor. The compressor takes in air at around 2,100 pounds per second from the outside and spins it along a shaft. That shaft gets narrower and squishes or pressurizes this air until it is very packed together and at a very high pressure. This pressure is very important for the engine because this is where a lot of that power we were talking about comes from. In fact, this compressor is so powerful that it could suck in all the air in a football stadium in about 1 minute. Now that we have that pressurized air, it goes through some tubes into the combustion chamber. The engine then mixes that high-pressure air with fuel, and then that mixture is ignited or combusts. The burning of this mixture creates really hot, expanding gases that then leave the combustion chamber and move to our next component, the turbine. All those hot gases leave the combustion chamber and go through the turbine. All that airflow causes the turbine to spin around really fast. This turbine is actually attached to the same shaft as the compressor, so once the engine gets going, this turbine can save energy by helping spin the compressor thanks to the hot gases flowing through it. And finally, the gases exit the engine through the nozzle at the end of the engine. As you can see in the graphic on the screen, when the nozzle opens up, it lets all of the hot gases out, which creates thrust. When the hot air in the engine meets the cold air outside of the engine is pushed forward. Much like a balloon that flies forward when the air is let out of it. The nozzle will expand and contract based on how much air has to come out, which creates force in the opposite direction, allowing the engine and anything attached to it to be thrust forwards. When you put all of these things together in order, you get one complete engine. This produces thrust, which will push the plane or device forwards. So first, the cold air comes into the compressor and is pressurized. That then travels into the combustion chamber where it mixes with fuel and ignites. These hot gases then go through the turbine to help the compressor save energy, and finally the nozzle opens and we have liftoff. So now that we have discussed the parts of the engine, let's talk about how these engines are tested. Once engines are designed and built, they have to be tested for a variety of reasons. The first and biggest one is safety. When these airplanes are up in the sky, they encounter all kinds of weather conditions. Can anyone tell me what kind of weather these engines might have to endure? Wind, rain, hail, snow, etc. Exactly. These weather conditions all could be very dangerous to the engines, and so they go through a ton of testing before they are cleared to fly. On the top left, you can see that chunks of ice and snow are being thrown through the engine to simulate what it would be like in a crazy hailstorm. They do the same thing with rain. Down on the bottom right, you can see that they are pumping 800 gallons of water through this engine per minute. This is way worse than any rainstorm, but they test these engines past anything that would ever actually occur to make sure they are safe. They also start the engines up in freezing weather or really hot weather to make sure they are able to fly under any conditions. Unfortunately, weather isn't the only atmospheric debris a jet engine might encounter. Can anyone think of what else an engine might have to handle in flight other than weather? Yes, birds. The same way they need to test for weather like hail and rain, they also have to test for birds. To check the damage on these engines, they will throw grocery store chickens through the engine to see how it holds up and make sure it can handle a small amount of birds just in case. Just in case these engines encounter an abnormally large amount of debris, the engines are tested to ensure that any malfunctions will remain in and slightly around the engine, making sure that nobody on the plane next to the engine is injured. Now that we know how an engine works and how they are tested to ensure safety, we can talk about the different types of engines and how they can be used. We have only really talked about one kind of jet engine, but there are actually several different types that are used for several different things. On the top left, there is a turboprop jet engine, which can be found in planes that have big propellers in front, giving them thrust through the spinning of those blades. On the top right, we have the turbofan, which is the same as the engines we discussed earlier, but it uses a fan to blow cold air along the side of some components, cooling them down as the engine runs, as well as increasing the thrust. The final type is on the bottom and is called a turbo shaft. Can anyone tell me what they think this engine is for? Helicopters. These engines are used in all types of industries. Helicopters are used heavily in the military and news industries to accomplish otherwise impossible jobs. On the bottom left, you will see that there is a machine that can take an engine and use it as a power source. A single engine produces enough energy to power roughly 40,000 homes. This generates a lot of power, but jet fuel is very expensive, and so it would typically be used in an emergency situation. In the oil industry and shipping industries, they use these engines and designs to power huge ships, which allows a lot of the trade industry to thrive thanks to fast shipping times and relatively low costs. These engines require a lot of engineers to work on them and ensure that they are safe and work well over time and many uses. The first type of engineer is a mechanical engineer. They work on the overall design of the engine, creating the blueprints and testing different designs and shapes for all the parts of the engine. They make sure these engines run efficiently and aren't too bulky or heavy for flight. They work together with the aeronautical engineer, who is a specialist in flight and how much force it takes to get these engines and anything attached to them off the ground. This affects the design and how much power these engines need to generate based off of weight regulations and estimations of what planes they will be putting in the air. These engineers also talk to chemical engineers, who do a lot of work to make sure the combustion that we discussed happens safely and in a controlled way. They run tests and calculate exactly what is going on and what chemical reactions will be occurring inside the engine. Electrical engineers run all the wiring that goes into running and controlling the engine. We didn't talk a lot about it, but the pilot has to be connected to these engines to change the speed of the plane. These connections are made through lots of wiring and electrical signals from the cockpit to the engines. Materials engineers also play a huge role in these engines, helping determine what materials are durable and lightweight so the engine can be more and more efficient without risking any safety or stability. They also need to find materials that can withstand many weather conditions and temperatures from the combustion within the engine itself. Finally, manufacturing engineers work on these engines and mainly the creation of these engines from start to finish. They are given blocks of material and need to create fast and effective ways of machining and creating these strong, durable engines that can take you anywhere in the world. As you can see, it takes a village of engineers to put together these engines, and we are always looking for more ways to make these engines more powerful and safer than before. The less fuel we need to power the engine, the less expensive material, and the less weight of the engines, the better they will be, and these improvements are being made every single day. So today, you all will each be building your own jet engine turbine. If you remember from earlier in the presentation, the turbine turns as the hot gas goes through it, saving energy and helping the compressor spin faster with less fuel. In order to do that, engineers have to design turbines that will spin as fast as possible. We will give you the option of a few different materials, and using your material engineer mindset, you will choose what you want your turbine to be made of, and then measure and cut out your very own turbines. Thank you for watching this video brought to you by the RPI Engineering Ambassadors. Hi, my name's Emily from the Rensselaer Polytechnic Institute Engineering Ambassadors, and today I'll be showing you the hands-on activity for the jet engines presentation. So to start off with, what we'll be doing for this hands-on will be building a turbine. So the students in your class will get the materials that they choose and build a jet engine turbine. We explained what a turbine does in the presentation, and so essentially the students should be able to recall that information, but if you'd like to go over it again, basically what a turbine is it's this fan that's inside of a jet engine, and it catches the hot gases that come out of the combustion chamber, and because of that it will spin rapidly, which will aid in the spinning of the compressor and actually saves a lot of energy. So what you want your students to do is create a turbine that will spin as quickly as possible, and you'll be able to test this as well at the end once they're done with their turbines. So you want to have a lot of materials in order to do this hands-on. All these materials you'll be able to buy at a local supermarket or craft store if you need, but we want to start with paper plates, aluminum foil tins, like pie tins. We have straws, pipe cleaners. We also have a Sharpie to mark the turbines later on, as well as lots of scissors because you want each student or each group that's making a turbine to have at least one set of scissors. We also want to have tape because mistakes do happen and sometimes you want to repair or change your design. We also have a timer. You can use your phone or a student's phone if you don't have one, as well as your computer. And then a pencil with an eraser similar to this. Make sure it has a good eraser because what you'll be doing is putting a push pin or some sort of sewing pin into the eraser. So this is very important because this is going to be how we test the turbine later on, but make sure that it goes in there and it stays in there relatively securely. And this works very well and it's very easy because most classrooms do have push pins or tacks in their room. So what we want to start off with is splitting the children into groups or the teenagers into groups. If you do have a large class size, you can put them in groups, but if you have a smaller class, each student can make their own turbine. It also depends on your time constraints. So what you want to start with is offering them the choice between the paper plates and the aluminum foil pie tins. This is important because this is getting their materials engineer mindset to work a little bit to decide which material would be more sturdy, which one would catch the most air, and most students will wind up choosing the aluminum foil pie tin. This is because they're easy to bend, they're easy to work with, and they're not as flimsy or delicate as the paper plates can be. So what most students will start off with doing is cutting off the outside edge, but what we want to do before anything else, this is very important because this comes into play later. You want to take the pin that you have, the push pin or the sewing pin, and you want to put it through the center of the pie tin. So find whatever center there is. This also works with paper plates, and just gently and carefully, so you don't prick yourself, push it through the center of the pie tin. So you'll see it goes, make sure it goes all the way through and that you don't create like too big of a hole, but you want to just make sure that it goes through and that you can actually kind of hold the tin like this. So once you do this, make sure you tell the students not to cut through this hole because you need it later for testing. Also make sure that they don't cover the hole because then you'll have to poke a new one and that can get a little iffy. So once the students have this, make sure that you tell them to come up with a plan, make a design. Some students do actually use pencils or markers to draw out what they'd like to do. A lot of students will just cut into their pie tins or their paper plates without thinking about it first, and then they'll make a mistake and want to make another one, and that can use up a lot of extra materials. So we try and stick with only having one pie tin or one paper plate per group or per person. So again, the first thing that they'll do is cut out the outside edge. So most students do that because the outside edge is bulky and can get in the way. It's not as smooth as the rest of the pie tin. But you do want to make sure that you tell students that when they cut the aluminum foil, it can be very sharp around the edges. And so you don't want them to get any paper cuts or any aluminum foil cuts on their hands, because that can be obviously dangerous. We don't want any injuries. So for the most part, it is safe to use aluminum foil. Just make sure that you tell them not to play around and make sure that they're safe. And if it makes you feel better, you can go around and take any excess that they cut off and move it to the side or throw it out, so they're not playing around with the extra, or so that they don't accidentally cut themselves on any of the pieces lying around. So once we have this, a lot of students, what they mainly do is copy the graphic that's on the screen. We do have a fan graphic, like a turbine graphic, on the screen while they're doing this. So if they can't think of anything, they shouldn't be discouraged. They can just try and mimic that. So we'll do that now. And a lot of them will just cut fan blades like so, making sure, again, not to cut through that hole in the center. We don't want to cut through it because then we won't be able to test it later. And the big variation is how many fan blades they make, how thin the fan blades are, how wide they are, and then what they do from here. So as an example, we can just bend these like so that they'll catch the airflow when it comes towards the fan and just push the fan in a circle. So this is the main idea. We want them to get to this point. It's very useful. It works very well. It's not the most creative answer to the problem, but it will work. So when in doubt, you can guide them towards this design. So now that we have a very basic turbine, what you'll want to do is test it. So when the student is done making their turbine, they're sure they don't want to make any changes before testing it for the first time. They'll come up to you in the center of the classroom, and then you can test it. So once the students are done with their turbine and they come up to the center of the classroom, you should have an industrial box fan set up in the center or on the side of your classroom, wherever the outlet is. And what you'll want to do is first you'll take their turbine and ask them which side they want to face the airflow. So the air is going to be coming up from the box fan, and so if they want the air to catch in the turbine, it's going to want to be held like this. So what you'll wind up doing is putting the pin through here and holding the pencil above the fan, above the turbine itself. So before we do that, we want to mark one of the fan blades. This is because when we're counting revolutions per minute, we need to know for sure which fan blade we're counting the revolutions on. And this will make it a lot easier visually for everyone who's counting. The students like to count too, so it's important to make sure it's very visible. So you can see on here, you can definitely tell the difference between the marked fan blade and the unmarked fan blades. And as these turbines get better and spin quicker, it'll be much harder to count accurately. So this is where this becomes really, really important. You want to make sure that you can count how many revolutions their turbine is actually making. So now that we've done that, you'll take the pin out of the eraser and you'll put it through so that it's pointing away from the fan. So again, this is why we made the hole in the beginning, and it's very important to be careful because these are pointy, so you should definitely have a teacher or assistant do it. But once you have your turbine secured like so, it shouldn't be falling off, it shouldn't be super flimsy, it should be relatively secure. And then what you can do from there is you'll bring over your box fan, And then you're going to want to start this on the lowest setting, because the airflow is different in certain areas and certain situations. So you can start it on the lowest setting, and then find a good spot where the airflow is strong so that the turbine catches as much wind as possible. So you'll notice that if I put it over the center, it doesn't spin as quickly. That's because this is a bit of a no airflow zone almost. So we move it outwards so that it catches more airflow. So from here, you're going to want to use that timer. So we want to count revolutions per minute. But if you have a long line of students, you have a lot of students who want to test, you don't have to test it for an entire minute. You can test it for 10 seconds and multiply it by 6, or you can test it for 30 seconds and multiply the revolutions by 2. So we're going to test this one, and you can actually see it is spinning decently well, but you can definitely see the fan blade that we're going to want to count the revolutions on. So you'll start your timer and then count how many revolutions. So 1, 2, 3, 4, 5, 6, and that's 6. So this turbine did 6 revolutions in 10 seconds. And so you'll multiply that by 6, so that'd be 36 revolutions per minute. That's pretty good considering it's our very quickly made turbine. But what we might want to change, you can make suggestions to the students as to what they might want to change on their turbines. Maybe this is a little too heavy. There might not be enough room between blades for it to spin quickly for the air to get through. And so after giving these suggestions, students can go back and try again. Maybe they cut their blades too thin and they want to tape them so that they have larger fan blades. Or maybe it's too flimsy, and that's where you can use the straws or the pipe cleaners to support the blades so that they're stronger and sturdier. It's really up to the students' creativity, and that's one of the best parts about the hands-on activity. So a few examples of what students have made in the past. This one is clearly very flimsy. The fan blades are very thin, they're not very sturdy, and they're not really encouraging airflow in any specific direction. So this one might not even spin at all, and that's okay if that happens. That means that there's a lot of room for improvement. So that's very good actually, because then students can understand the process of trial and error as well as the design process, because it's very important that you continually test new ideas. So in this student's case, they actually went back and put pipe cleaners on the back to make it a little bit more sturdy. Again, they did block the hole in the center of their turbine, and that's important that students don't do that. Make sure you remind them again once they're done not to cover that hole, because it is very important. But in terms of this turbine, there was plenty of improvements to be made. Another one that we actually saw, which this one's actually my favorite, but this one's very interesting because it's not the stereotypical design that you notice in students. This one has a lot more fans in the center and allows for airflow through, but not too much airflow. And that actually became a problem with this student. When we were testing it, it would get pushed upwards because too much of the air was getting caught underneath and not enough could make it through this turbine. So there are always things that you can improve on these turbines. There are always things that you can do differently, and students really enjoy that challenge. I think one of the more entertaining things that we'll do is we'll test students and we'll kind of make it a competition in the classroom. So some students can come into groups, make team names, and then go against their peers so that they can see who has the best turbine, who has the highest revolutions per minute. And then if you want, you can offer extra credit or some sort of incentive to get them to work a little bit harder and test out new ideas. So thank you so much for watching. This has been the Jet Engines hands-on presentation. I'm Emily from the Rensselaer Polytechnic Institute Engineering Ambassadors, and thank you so much for watching today.